All right, this is the second video in a series of 2 videos addressing inverses, inverse trig functions, if you will. So again, we've got a few examples here on the screen, and this screen is just going to be a reminder for you. If you need a longer explanation of why these things happen, you can always watch the first video again. But basically, we want to be able to find or evaluate inverse trig functions. And what we have to remember is both the domains and the ranges often are restricted for these functions. When we talk about an inverse sine, remember that it always exists on the right side, right? My hint to you previously was Santa's cap. Sine and inverse tangent, they're sort of on Santa's belly, right? Santa, S and T. So again, the inverse sine of 0, well, the sine of x would have equaled 0 when x was 0, right? Sine is 0 at 0. So again, I'm going to say that the answer to this one is just going to be 0, because 0 radians or 0 degrees, and notice they didn't specify on here, so we better say, well, if we're saying 0 degrees or 0 radians, we'll probably operate in radians most of the time here. But again, the answer would be at 0. The inverse tangent, on the other hand, again, it would be equal to -1 whenever the tangent of x, right, would have equaled -1. Well, remember, tangent is always sine over cosine, or basically y over x. We'd be dividing two things, and the only reason you would divide and end up with -1 is if you had equal measurements left to right as what you do top to bottom. In order to be negative, one of these, right, needs to be negative, or basically we're going to be down here in quadrant 4. Now remember, we want to go directly toward that measurement though, so in order to get directly to that line, what we would say is the inverse tangent of -1 would be a value of -pi over 4, or at -45 degrees, if you will. Inverse cosine, well, now remember this is Santa's cap, so again we're going to be on the top of our unit circle. Cosine would only be negative, right, or a -1 value. Cosine normally starts at, at 0 radians, it would be +1, while at pi radians, you'd be at -1, right? Or if you want to think of when we're graphing, right? Sines start at 1 and then they sort of loop down and up, right? Kind of doing that periodic curve. Well, in this first portion of the curve, right? Here to here, the place that we want to be is down here at -1, right? So again, that's going to happen at pi radians. Inverse cosine of -1 would give you back an answer of pi radians. And then finally, the arctangent, again, it would be helpful to kind of think of where would √3/3 have come from? Well, remember that √3/3 is the same thing as 1/√3. Okay? If we re-rationalize, we multiply by √3 both top and bottom, you would have had 3/3√3, cancel the 3's is 1/√3, and the only reason we would have been, tangent being positive, again, if we think about our Santa's cap, tangent's only positive up in quadrant 1, right, or down in quadrant 3, but again, we don't want quadrant 3. But we're going to be 1 unit, right, opposite over adjacent, 1 unit up, √3 units out. Looks to me like that is pi over 6 radians. Okay? Pi over 6 radians. Again, 1 unit up, √3 units to the right, pi over 6 radians. Now, those same ideas can help us when we do what we call our composite trig functions. Tangent and arctangent, let's just start going through examples here. In option A up here, or that first problem anyway, the tangent of the arctangent should just cancel away. And we can actually check our answer. I do believe the answer to the tangent of the arctangent is -5. Because basically that's perfectly fine. If we think about it, arctangent of -5, or -5 radians, right? The arctangent at -5, or sorry, for a ratio, if I drew a picture here, right? And tangent would have only had a negative ratio actually down in quadrant 4 here. But again, if we said -5/1, again, we're going to get an angle right here we could call theta, right? But immediately we're going to find the tangent of that angle, which immediately brings us right back to -5. Let's use that same idea down below here for option B. Arc cosine of the cosine at 5 pi over 6. Well, if we picture it, right? The cosine at 5 pi over 6 is going to be over here, right? Which would essentially be a 30-degree reference angle or a pi over 6 reference angle. And if I want to find the arc cosine of that exact same triangle or that exact same measurement, right, x over r, well, the cosine exists in quadrants 1 and 2, right? That's that Santa's cap, right? The cap, the top part, which means that our answer, very simply, well, the arc cosine and the cosine cancel each other away, and 5 pi over 6 is our answer, right? It makes sense. Arc cosine, cosine, they cancel away. Let's look at one that's a little more tricky. Arc sine of the sine at 5 pi over 3. Well, 5 pi over 3 takes us all the way around down here. It's going to be a pi over 3 reference angle. But again, it's a 30, 60, 90 triangle, basically. So this is going to be root 3, or negative root 3, positive 1, and a root 2 up here. But now we have a slight problem. That would represent very well this idea, right? The sine of 5 pi over 3 would essentially be, right, opposite over hypotenuse. This would be saying, let's find the arc sine of negative root 3 over 2. Well, what you want to remember is the arc sine only gives you answers between negative pi over 2 and pi over 2. Now you might be saying, well, wait a minute, we're in quadrant 4. That sounds great. But the difference is I don't want to go around the unit circle this direction, right? My 5 pi over 3 in order to get there. I want to go directly, right, downwards. So instead of 5 pi over 3, our answer to this one is actually going to be negative pi over 3. We want to go directly to our answer. Arc sine, right, has to go directly downwards to the angle. So the answer can't be 5 pi over 3. It has to be negative pi over 3. And finally, on this last one, well, you might remember that inverse cosine of pi, well, there's going to be a slight problem there. I can't even start that problem. I can't take the inverse cosine of a number that's greater than or less than, right? Greater than 1 or less than negative 1. So again, pi is too big. So that problem can't even be done. Very simply, that one doesn't have a solution. Inverse cosine of pi doesn't exist. Always start with that inside function, right? When you're looking at these, represent your picture using that, and then see what happens when you try to find that outside function. Composition, start with the inside function, work your way out. Let's look at a couple more very quickly. The same idea will happen here for these functions. If I'm looking at the arc cosine of 2/3, the first thing that I would do, again, is remember that the cosine, again, is going to be a positive value up in quadrant 1. So I'm going to draw myself a triangle up here where the cosine would have been 2/3, which means I'm probably going to need to do a little Pythagorean theorem because now I want to find the tangent of that same angle, right? If we called that angle theta, the arc cosine of 2/3 is essentially what we're calling theta. It's going to get us an angle. Now, you don't need to find that angle. We just need to find the tangent of it, which means if we said 3 squared equals 2 squared plus, let's just go ahead and call it y squared since we're going upwards. 9 minus 4 will be 5. And if we take the square root, this would have been root 5 up here. And the tangent then is opposite over adjacent. We have our tangent. We can check our answer very quickly there, right? Again, we're finding the tangent for the picture set up by the arc cosine, right? The triangle was set up due to that arc cosine value, arc cosine of the ratio, right, 2 to 3. And then we want to find the tangent at that same angle. Let's do the same thing over here at the right. Arc cosine of 3x, or what you could kind of picture as 3x over 1. Now you'll notice they said that x has to be between 0 and 1/3, which means we're doing the arc cosine of a positive number, right? 3 times 0 or 3 times 1/3 is at most 0 to 1. So basically we're going to be up in quadrant 1 again. Let's just draw ourselves a simple quadrant 1 triangle. Cosine being again adjacent over hypotenuse. But if I want to find the sine, I'm going to need the opposite. So again, 3x squared would be 9x squared plus the other leg, let's call it y. Right? is equal to 1 squared. Y will be equal to 1 minus 9x squared. And finally, again, that's y squared, sorry. Finally, we'll take our square root of both sides, and basically y would end up equal to the square root 1 minus 9x squared. Square root 1 minus 9x squared. Well, now the really nice part is the sign is just opposite, so that value over 1, or basically the square root of 1 minus 9x squared. And we'll just double check our answer very quickly to make sure there's exactly what we get. Again, the number one major way to do these, draw yourself a picture. If you can picture what's happening inside the composed function, then you can use your picture, use your diagram to find what happens on the outside. If you have any questions, talk to your teacher. Otherwise, have a great day.